Hello, my name is Sheridan Ingram. I'm a student at Dallas Baptist University, and for this REU program, I've been paired with Shreya Saman. Our topic is Communication is Key, integrating fault analysis and functional requirements for safety-critical software. You might have a few questions, like what are functional requirements? Well, functional requirements are what we want the software to do. So they're headed up by our design team, they meet with the client, they detail everything that they want the software to do, and this is placed in a legal contract that they are now bound to fulfill. Fault analysis, on the other hand, is what we do not want the software to do. So this is headed up by our safety team. They get together and outline everything that could possibly go wrong with our software, and the goal is to identify undesired events that could lead to loss of life or damage to property. Now, what is safety critical software? Well, safety critical means that we're dealing with systems that, in the event of failure, could cause harm to people, property, or the environment. Software is now being used in these safety critical systems more than ever and has absolutely exploded over the last 50 years. Examples of such systems include MRI machines, insulin pumps, missile targeting systems, airplane navigation, and railroad crossing systems. Safety critical software requires that functional requirements are fulfilled in the worst possible conditions while minimizing loss of life and damage to property upon failure. So what's the challenge? Well, the challenge is that in our current industry, the design team and the safety team don't typically communicate. There's no common standard for communication between the two teams, and both teams can be very large, up to 100 people or more in either side. This lack of communication can result in a system that doesn't fulfill functional requirements, and those violated functional requirements that could result in legal action, or it could result in undiscovered hazards that result in loss of life or damage to property. An example of the miscommunication between the design team and the safety team could be seen in the safety critical software for an insulin pump. So the safety team detects a potential hazard. When the battery is changed, the timer for the pump resets and an extra dose of insulin is administered immediately. The design team moves ahead unaware of this hazard in their system. Two possible scenarios could result from this. Scenario one is that the design team continues unaware, the insulin pump makes it to production with the hazard intact, and that extra dose of insulin could result in major injury or death of a patient. This is a less likely scenario though, because safety critical software does undergo a fair amount of testing. Scenario two, which is more likely, is that the safety team creates a recoverability for the hazard, but it violates the functional requirements for the system. So a real-world example of this would be that a fail-safe is created, but no insulin could be administered on the restoral of power, which could still violate the patient's schedule for insulin, which therefore violates the functional requirements of our system. So what's the solution to this? We propose the integration of fault analysis and functional requirements to identify testable interactions between the intended behaviors and the hazardous conditions. To describe the functional requirements, we will use Petri nets, and to describe the fault analysis side of things, we will use fault trees. This will result in a safer, recoverable model that will confirm that the functional requirements are fulfilled in the worst possible conditions, minimizing loss of life and damage to property. We chose fault trees because they're the industry standard for safety critical systems, and Petri nets because they're simple, scalable, and able to model parallel processes for multiple different states.
Hello, my name is Shreya Saman, and I'm a senior at the University of Texas at Dallas, and I'm going to introduce our case study. Let's look at a railway crossing system that functions like so. As we can see in the image, there's a train on a single track, a gate, and a semaphore that controls the behavior of the train within the intersection. If there's no train within the intersection, the gate is up and the semaphore is red. When the system detects the train approaching, the gate begins to move down and the system signals the light to change. The lights change to green and the train is now within the intersection. When it is time for the train to leave, the system begins to reset its gate and semaphore systems, bringing the gate up and changing the light back to red accordingly. We see that this system reflects the following functional requirements. There is a gate system that controls the train's entry into the intersection, allowing the train to leave when it turns green. The system also has sensors to detect the train's arrival and departure. As for the fault analysis of the system, we notice that a collision may occur if there is a malfunction within the gate and the semaphore systems while the train is within the intersection. If the gate moves up and the semaphore turns red due to a power surge, The train within the intersection can get stuck, which can cause a collision if another train approaches the system. There are two ways in which this will be handled. The safety team could just choose to ignore the hazard and go to production, which could cause the loss of life and damage to property. This is highly unlikely. Let's assume the safety team catches the hazard and creates a recoverability method like so. Upon the restoral of power, default the system to return to the original state of the gate down and the semaphore red. However, this method ends up violating functional requirements because the light would never turn green and the train would remain stuck. Our solution is to integrate these two systems. Let's model our system based off of functional requirements with a Petri net. A Petri net is composed of circles that indicate places, rectangles that act as transitions between places, arrows that connect the two, and tokens which indicate that certain places are active. Note that the transitions help the tokens move from one place to another, creating different system states every time fired. Only one transition fires at a time and consumes and produces tokens according to the incoming and outgoing arrows. Functional requirements are reflected within the Petri net. The automatic gate system is modeled by places P2 and P3, while the semaphore system is modeled by gates P6 and P7. The behavior of the train on the single track system is modeled by places in the middle of the Petri net, P1, P4, P5, and so on. Let's walk through the Petri net. State 1. The train approaches the intersection, the gate is up, as you can see by the token in P2, and the semaphore is red, symbolized by the token in P7. Transition T2 will then be triggered as the train shifts into the intersection, which then gives us state 2. The gate is now down, the lights have been signaled to change, and the train is entering the intersection. Transition T4 will then be triggered, and the light will then change to green, as we can see in the next state. State 3. The semaphore is green, the gate is down, and the train is now in the intersection. When it is time for the train to leave, transition T6 will be triggered to signal the gates and the semaphore to reset, which gives us state 4. The train now leaves the intersection, the gate is down and the light is green. We reset the lights first by triggering transition T5. Then we reset the gate by triggering transition T3, which gives us state 6, confirming the gate is up, the semaphore is red, and the train has left the intersection. T7 is then triggered, completing one iteration of the system. Let's now model the safety hazard using fault trees. The rectangles represent hazards. The gates in the middle of each layer represent AND or gates. The rectangles represent hazards. The gates in the middle of each layer represent AND or gates, while lines connect these gates to the hazards. Here's how this works. The hazard at the top is broken down into a series of lower level hazards. We can see that the collision is caused by the crossing not clear and the train in the intersection. The lower level hazards are broken down until they cannot be simplified, giving us a fault path of the top level hazard. Let's take a look at how a collision occurs within our system. A spurious electrical signal from a power surge turns the light red and brings the gate up. This results in the crossing not clear. If there is a train in the intersection and there is a train approaching the intersection, we have a collision on our hands. We can see this modeled with a fault tree in the next slide. Now we're going to talk about integrating the two systems.
So before we get into things, we need to introduce what a system state is. A system state is a representation of a particular combination of tokens and places. Basically, it just tells us what's happening in the system at a given point in time. Here we have our state table, which gives us all possible combinations of token locations, i.e. our place markings that our system can go through. For example, here we have S0 with the place marking P2, P7, P11, which corresponds to, in our Petri net, gate ready to go down, semaphore ready to turn green, and our final state. When you look at our Petri net on the right, you can see that there are tokens in each of the places P2, P7, and P11. So the first step in our integration process is mapping. Step 1 of mapping is identify the lowest level of hazards in our fault tree. So here we have them in green boxes. They're the low level hazards in our fault tree of gate up, semaphore red, and train in intersection. Step 2 is to use keyword matching to identify the place markings in the Petri net that correspond to that singular hazard. So for example, gate up corresponds to P2 in our Petri net. Step 3 is to put a token in that place marking on our Petri net. And then we repeat step 2 and 3 until all lower level hazards have been represented. So gate up corresponds to P2, semaphore red to P7, and train and intersection to P5. And as you can see, there are tokens in each of those locations in our Petri net. Therefore, our hazard state is P2, P5, P7. So from mapping, we know that our hazardous state is P2, P5, P7. After analyzing our state table, we can see that this hazardous state does not actually occur in our Petri net the current way that it is modeled. The fact that it doesn't occur indicates that the hazard was undetectable to the design team before this point. So to communicate the hazard to the design team, we can model this hazard using failure transitions. To add failure transitions, we add F3 and F5 marked by those double lines to model our power surge failure. F3 models the surge moving the gate up, and F5 models the surge turning the semaphore red. Now that we have our hazard modeled, R1 is going to model our recoverability method. Because now that we have our hazard, we need to know how we're going to recover when we end up in that state. So real-world representation of this recoverability would be a sensor in the intersection that's going to assume that the gate is up and the light is red and just automatically resend a reset signal to move those down and to change your light, adding a layer of redundancy. In our Petri net, when our system reaches our hazardous state of P2, P5, P7, it's going to move the misplaced tokens to their respective places and then just cycle the token through P5. And that brings us to our final integrated diagram, our PNFI, our Petri net with fault integration. Now the design team is aware of our power surge hazard in their system that could cause a loss of life mishap. This was undetectable during our original design, and it was not visible until we performed the integration. And our safety team can ensure that their recoverability does not violate the functional requirements of the system. Previously, their recoverability method involved turning the semaphore red as a default setting. Now they understand that the semaphore must be turned green in addition to the gate being moved down. To evaluate the success of our PNFI, we create a reachability graph with pipe 2. That's this fish-shaped diagram that you can see on the right. We evaluate success by measuring that all states that do not result from failure transitions have a path to the original state. Second, all states that do result from failure transitions should have a path including a recoverability transition that results in our original state. So in evaluating our system, our original state is S0, and all states that do not result from failure transitions do have a path back to our original state. So if we map our transitions through the loop on the left, we can see that we have a beginning at S0, we follow our transitions all the way around, and we will return back to S0. F3 and F5 on the right-hand side represent the failures of the gate and the semaphore, which result in S10, which is that hazardous state that we've been talking about, the P2, P5, P7. But we can see that we have this recoverability transition that we built in, and it brings us back to S3, which is our recoverable state because it has a path back to S0. Because both conditions are fulfilled, our PNFI is considered successful. Now we move on to testing the system. So why are test scenarios important? Well, test scenarios ensure that our system, recoverability included in the real world, fulfill their functional requirements in the worst possible conditions. This could be done manually, but that can be a challenge with large systems and can result in incomplete coverage. Additionally, you need experts that are familiar with your domain and system. Therefore, our goal is automatable test generation with demonstratable coverage. Our approach is an adaptation of model-based testing based on one of our papers. The process is to run an all-pass BFS on our reachability graph, starting at S0 to get a BFS tree, pictured here. This is the same reachability graph from our success slide. Recall that S0 is our starting state of P2, P7, P11, and S3 is our recoverable state. The result of this process is we get multiple sequences of states that result in test scenarios with demonstratable coverage. Paths that cover all possible states of our system can be generated. The goal is to test the real-life system behaves in the same way that our model does. The different types of test scenarios that will result from this process are hazard test scenarios, which will follow from the hazard transitions, which are pictured here in red, and their goal is to complete a path from the original state to the recoverable state using recovery transitions. Standard test scenarios will contain no hazard transitions, and their goal is to complete a path back to the original state without including any hazard transitions. The results for both scenarios are a progression of states for hazardous and non-hazardous instances that are automatable and covers all possible states for the model.
Okay, yeah, let's talk about hazard test scenarios. So like Sheridan said, we have two hazard test cases, as you can see in green, and both of them start at S0 and they all end in the recoverable state S3. And as you can see, it kind of goes to a hazardous state S10 right here by taking the fault transitions, which model the electrical signals that push the gate up and turn the light red. But then we take a recoverability transition and we're able to get back to a recoverable state, S3. It does not get stuck here because from S3 you can just go right back to S0. So the train can eventually leave. And the other paths represented ending in S13, 14, 15, it's how the system would behave if we didn't use our recoverability, if we never put that in there. And that would lead to getting stuck in very hazardous situations. Next, we have standard test scenarios. It's just the one on it's the first branch of this little tree here. And it's, as you can see in green, we've got two paths going from S0 to S0, and they don't include any hazard transitions. And it basically, we cover all possible states for the system.
So what did we do and why did we do it? Well, in this presentation, we proposed an integration method for fault analysis and functional requirements for the purpose of safety testing. For our railroad crossing system, our integration approach was able to catch the collision hazard before the system made it to production, develop a recovery approach that did not violate our functional requirements, and develop test scenarios to rigorously test our system. We did this to prevent loss of life and damage to the property/environment and ensure fulfillment of functional requirements to avoid legal action. Going forward, we have a few different directions that we would like to take this topic. First, we would like to conduct a case study on a more complex real-world system. We would like to acquire a real-world Petri net and fault tree for our current safety-critical systems that are in production right now. This would allow more in-depth exploration, and we would like to apply a modular approach that would circumvent state explosion. We would also like to develop more comprehensive heuristics for our mapping process and integration process. This would be best achieved through the acquisition of the above-mentioned diagrams. Finally, we believe that large portions of our process could benefit from automation through tools. And I think that's everything. Thank y'all for listening.